All right, folks, let's get started. We've got things to do. So, the way I'm going to run the last two quizzes, we'll have a quiz on chapter 13, but I'm going to have you upload that through Canvas because there's no way for me to get it back to you but before the exam. So, keep an eye out this afternoon for that. You'll basically take a picture of it, upload it into Canvas, and that way I'll grade it. Your last quiz, quiz 14, will be a quiz that will basically ask you to comment on a few things. It won't be over any chemistry content per se. And then the review for the final exam will be Monday at 5:30 upstairs in 411, where we've had all of our previous reviews. It will go to however long we need to, but my plan is to come in, bring the old exams, at least electronically. I will start with exam 1. I'll throw it up. You all can bring your stuff with you. I'll scroll through it, and when you all have a question, we'll stop and we'll work on that question. So we'll do that for exam 1, 2, and 3. Okay? There will also be a poll that will be coming out this afternoon about how you want your final, whether you want it to be a 50-question final or a 75-question final. Both would be worth 150 points. It's just if it's 75 questions, right, they're worth 2 points apiece. If it's a 50-point question or 50-point exam, then it'll be, or 50-question exam, it'll be 3 points apiece. So just something for y'all to think about. All right, so we finished talking about carboxylic acids last time. We talked about the general structure of carboxylic acids. We know a little bit about these different types of things. We talked about these, nomenclature, how we name them. I think you're all up to date on that. Find the longest chain, use the oic acid. We talked about some of these less common names. So malonic acid, oxalic acid, succinic acid, etc. We talked about a lot of those last time. We started talking a little bit about physical properties, of course, right? And the fact that carboxylic acids, at least in their pure form, like to form these dimers, so-called dimers, and so it makes the molecule behave as if it's heavier, and so we've found that carboxylic acids have higher boiling points and different physical properties like that compared to what you might expect given their molecular weight. Yeah, we talked about some of that. So what we didn't get to talking about were lipids, and so this is a class of carboxylic acids that you're going to need to know when you get into biochemistry. These names obviously have meaning, but they're not derived systematically. They're derived more from where they've been discovered, and so, or how they were discovered. And so these are common lipids that are, you know, you all have these in your body. These are used to make fats. They're used to make lipid bilayers. This is what your cells depend on to have the cell membrane, are these types of fatty acids, and then there's derivatives of them as well. But you can see arachidonic acid, you can see oleic acid, linoleic acid, palmitoic acid. What's the difference between all of these acids that I've just mentioned, the arachidonic, oleic, linoleic, and palmitoleic? Yeah, the number of double bonds are different, right? And so palmitoic acid is an unsaturated fatty acid, and oleic acid is an unsaturated fatty acid, but linoleic and arachidonic are polyunsaturated fatty acids, right? And so you all have learned probably in other classes that polyunsaturated fatty acid, or PUFAs, are healthy for you, right? So when you eat good olive oil and things like that, you're digesting and you're intaking polyunsaturated fatty acid. These are the acids that are considered responsible for good health. What else is common among all of those 4 unsaturated fatty acids? What about the double bond? All the double bonds are what kind of configuration? They're cis, yeah, all of them are cis. Nature likes cis polyunsaturated fatty acids. They are typically liquids at room temperature, at body temperature, okay? Whereas the trans fats, here's an example of oleic acid. It is a trans unsaturated fatty acid. Trans fats you might be hearing about in the news are unhealthy for you, right? Imagine that, just going from a cis double bond to a trans double bond, healthy, unhealthy, right? And it turns out that the trans double bond being more stable has this particular shape, and it can pack and it can form solids a lot easier. And you don't want solid stuff falling out of your blood, right? That forms plaques. Those plaques, clog arteries. Clogged arteries lead to heart attacks. And then, of course, stearic acid. That is, how would you call that one? How is that different from all the others?
Saturated.
It's a saturated fatty acid. And what do we know about saturated fats?
Solid.
They're solids. It's typically the lard that you go buy. It tastes good probably, but it's not as good for you, right? So saturated fatty acids are what you might think of as greases. Quite a bit of time. All right, so in terms of acidity, you all learned a little bit about this probably in Chemistry 106. We talked a little bit about this at the beginning of the semester. This idea of equilibrium constant, right? Products over reactants. So if we take a generic carboxylic acid, place it in water, it will dissociate a little bit, not completely. And so you can actually go into the lab and you can measure the concentration of the H3O plus that gets formed, the acetate anion in this case, and the intact acid. You can figure those out pretty easily. In fact, you can figure them out by NMR. And so KEQ is equal to that's KEQ. Now, what do you think about the concentration of water? If let's say I take acetic acid, I'm gonna make a really dilute vinegar solution. So I take pure acetic acid, let's say I take a liter of water, and I add maybe half a milliliter of acetic acid to it. What do you think happens to the concentration of water? Does it change significantly, do you think? What do you think? I take a big flask of pure water and I add just a tiny amount of acetic acid to it. What do you think is going to happen to the concentration of water?
It would decrease somewhat, but not substantially.
Not substantially. And in fact, almost immeasurably. So it remains relatively constant over most things that we do. And so anytime things remain relatively constant when you're talking about these types of things, you could move them out of the equation, so to speak. Okay? And so if you take KEQ and multiply it times the concentration of water, you get a new equation, which is CH3CO2 minus H3O plus divided by the acetic acid. Okay? Good enough with that. And it turns out this is equal to what's called Ka. This is the acidity constant. You might have learned in high school if you took chemistry, you might have learned in general chemistry here or somewhere else, that water falls out of the equation. It does not fall out. There's no such thing as something falling out of an equation. I don't know why we tell you all this nonsense. And we tell you this in math, when you take math classes. It doesn't fall out of the equation. We move it over here because it doesn't change at all. And so it just becomes a new constant. Ka is not equal to Keq. Ka is equal to Keq times the concentration of water. Okay? But you might have learned in the past, oh, well, it's Ka is equal to Keq, just drop out the water because it falls out of the equation, because it's a pure liquid and doesn't go into it's nonsense. We mathematically remove it, move it over to the other side and call it a new constant to make life easy for us. Okay? And so these acidity constants tell us something about the equilibrium. If the equilibrium lies far to the right, the equilibrium constant, or the Ka constant, would be large. If very little of the acid dissociates, the Ka constant would be very small, right? Because products over reactants, if I don't have very much of this, that means this is big, this number would be small. If it goes to completion, where everything up here is big and this is really tiny, this number would be very, very large. Okay? These numbers are so large and so tiny, depending on the type of acid you're working with, that it becomes unwieldy to deal with. Nobody wants to write 0.000000001, right? Nobody does that. So what do? We take the negative log of it and call it pKa. Simply just take that number, and that gives us numbers that we can deal with. And it turns out that most carboxylic acids are going to have a pKa, most, not all. Most are going to have a pKa between 4 and 5, meaning that they're weak acids. Strong acids have pKa's that are negative. Okay? But if you have a pKa that is positive, that means you're a weak acid, relatively weak acid. Okay? So these are weak acids. We've already talked about that. I'm going to skip that for today. There are a couple of reactions of carboxylic acids that you need to know about. One of them is called esterification. You can convert carboxylic acids into esters. So here's an example where we're taking benzoic acid. We learned about that last time. We treat it with sodium hydroxide. We know that acids and bases react to make salts in water. That's what happens here. I get the so-called sodium benzoate, which we learned last time was a preservative in soy sauce. If you read the back of it, you'll see that it contains sodium benzoate. It's a nice preservative, food preservative. But this molecule is actually quite reactive, and so we can react it with something like iodomethane, and we can make the ester. In this case, the so-called methyl benzoate. Okay? What kind of reaction do you think that is, that second reaction? And I'm not showing all the ions, doesn't matter. What kind of reaction? How would I push those arrows? What reactions have we learned? What reaction types have we learned this semester?
SN1,
SN1, SN2, E1, E2. Given what we have up there, is that going to be a substitution or an elimination reaction? It's a substitution reaction. I heard somebody whisper it. Don't be afraid, be brave. What kind of substitution reaction is that going to be, SN1 or SN2? It's SN1 that goes through a carbocation intermediate, doesn't it? Can I generate methyl carbocations? CH3 plus? Would that be a stable carbocation? No, it wouldn't be a stable carbocation, right? So it's going to be an SN2 reaction, right? So I've got a methyl group, I've got a good leaving group, I've got a good nucleophile. Oops. Okay. This is an esterification reaction. We're converting a carboxylic acid into an ester. This is a very useful reaction, not this particular one. But in general, this is a very good reaction. What do you all think, knowing what you know about carboxylic acids, do you think they smell pleasant or awful? Awful. Why do you say awful? Acetic acid vinegar. I don't know anybody gets ready to go out on a date and puts vinegar behind their ear, right? Or on their neck. Nobody wants to smell that, right? Turns out that body odor is butyric acid. That's the stench from body odor. Is carboxylic acids stink. I don't know of any of them that smell pleasant. But interestingly enough, the esters smell pleasant. Methyl benzoate right there is the odor that you smell when you smell some flowers. That is the scent of snapdragons. If you like snapdragon flowers, what you're smelling is methyl benzoate. Don't worry about the name. It's the methyl ester of benzoic acid. Okay? It attracts bees. It's a bee attractant. Why is that important? Pollination. Flowers have figured it out. I need the bees to help me pollinate. You know, I'm going to convert this benzoic acid into methyl benzoate. I'm going to attract them. They're going to get their pollen all over them, etc. Okay? It turns out that reaction that we just talked about, the SN2 reaction, is not the way that you would go about making methyl benzoate practically. Iodomethane is expensive. But you can do what's called a Fischer esterification. And that Fischer esterification is where you take a carboxylic acid and an alcohol and use a catalytic amount of strong acid like sulfuric acid. You simply boil it up and you make the ester. This is called Fischer esterification. Okay? And so esters are derivatives of carboxylic acids. We're not going to go through the mechanism of this. It's several steps. They're not tough or difficult steps, but this is real easy to do. You literally take a flask, put in your benzoic acid, dissolve it in methanol, add a drop or two of sulfuric acid, and boil it for about an hour. And you make synthetic snapdragon scent. And it smells halfway decent. Okay. There are a number of carboxylic acid derivatives that you just need to be familiar with. Okay, there's acid chlorides is one. Okay, you can make acid chlorides by taking any carboxylic acid and reacting it with thionyl chloride. We talked a little bit about this when we talked about electrophilic aromatic substitution. The Friedel-Crafts acylation reaction needs acid chlorides, right? And this is how you make them. You simply take the carboxylic acid and react it with thionyl chloride, and you get the acid chloride, and then you get these nasty gases, sulfur dioxide and HCl. You can't do this out on the open bench. You've got to be in a hood. HCl comes billowing out. HCl is quite toxic and corrosive. But nonetheless, we can make these acid chlorides very, very easily from carboxylic acids. And there are other reagents that do it, but we're just going to focus on thionyl chloride. Okay? All right. Chapter 18. Last stuff that we're going to talk about. This will be some of the first things that you have to know when you go into Biochemistry 1, or 420, not Biochemistry 1, the Survey of Biochemistry, Chemistry 420. Your instructor, Dr. Jacques Kessel, will expect you to know at least a little bit about amino acids. Okay? And so we're going to focus only on the alpha amino acids. These are the amino acids that come together to form your proteins and peptides in your body and in other biological systems. Okay? These are also, some people call these monomers because they link together to form proteins and peptides, which are polymers. Okay? These are not the kind of polymers, biopolymers are not the kind of polymers that you might learn if you took a class across the street, a general class across the street. These are very well-defined, structurally identifiable polymers. There's not a statistical distribution of things. Okay?
So does that include like collagen?
I don't know. I'd have to go back and look on that one. But probably. All of these amino acids, with the exception of glycine, are chiral. That's why you needed to know stuff in chapter 6. Okay? It turns out this is important. Okay? So obviously when R is equal to H, it doesn't have a chiral center. But if R is anything else, these become chiral. And in nature, you will learn, in this class you learned about R and S. In nature and in biochemistry, they're going to talk about D and L. It's the same thing, just biochemists make things more complicated for some reason.
Yeah, I'm just curious, what is the most defining feature regarding alpha amino acids?
What is the most defining feature?
Yeah, for notes.
For notes, the most defining feature is that you have functional groups that are polar opposites of one another. Right? You've got a carboxylic acid, and you've got an amine, which is a base. So you're incorporating acids and bases in the same molecule. That's kind of unique. Okay? And it gives rise to a lot of chemistry that we'll talk about. Here we go, the acid-base properties. When you take an amino acid and you place it in water, it is neutral for a generic amino acid. Okay? But it exists as a so-called Zwitter ion. It's German, Zwitter, not Zwitter. Zwitter ion. Okay? It is charged, but it is overall neutral. It is charged, but it is overall neutral. If I took an amino acid, let's just say that the R group is just CH3, and I place that in water, it will exist as this Zwitter ion if I place it in pure water. And that makes sense, doesn't it? I've got an acid and I've got a base. They're not going to just not react with each other, right? So what happens is that the proton on the carboxylic acid gets transferred to the basic amine, and you end up with this Zwitter ion. It is both positively and negatively charged. Okay? So it's charged, but overall electrically neutral. Okay? You are going to need to know for the exam your amino acids. I highly recommend that your notes contain the structure and codes for the amino acids that you see in your tables, in your book. Here's just an excerpt. Okay? So there are 20 common amino acids. You may have learned in high school that there are only 20 amino acids. Again, nonsense. There are an infinite number of amino acids. But there are 20 common ones that are important in biology. Okay? When you get to Biochem 420, you will have to have these memorized at some point. You will need to know the amino acids. Okay? Now, what you're looking at in your chart, you're seeing the name of the amino acid, and then in parentheses, you're seeing two codes. There's a 3-letter code for all of the amino acids. So alanine is ALA. It's usually the first 3 letters of the spelling. Glycine is GLY. But my good biochem friends typically like to, 3 letters is too much, so they take it down to 1. Right? And so there's also the 1-letter code. Quite frequently, that 1-letter code is simply the first letter in the spelling. So alanine is A, glycine is G, isoleucine is I. Leucine is L, methionine is M. However, that's about as far as it goes, so to speak. You start to end up with other ones. Phenylalanine, for example, is F, not P. Proline is P. That's why phenylalanine is F. Tryptophan is not T, it's W. Valine, V, that one makes sense. Asparagine is not A because that's what alanine is, so they pick N for that one. Glutamine, which is what we have here, isn't G because that's glycine, so they call it Q. Okay? So on and so forth. On my exam, we will only be focusing on the 3-letter codes. I use the 3-letter codes because I can remember the 3-letter codes. Okay? It's a lot easier for me to remember. Okay? So what is different among all of these amino acids? It's the R group. Each one has a different R group, and we can break it up into nonpolar side chains, right? A methyl group's not polar, an alkyl group's not polar, right? Those are all nonpolar side chains. We can have polar side chains. You're seeing those examples there. So they have polar groups. Okay? You all know anything about any of these amino acids?
Glutamine is naturally occurring in the stomach. And
Which one?
Glutamine.
Yeah, okay.
And it allows muscle recovery. A lot
Okay.
of people take it when working out, but but you don't need it unless you have a underproduction of it in your body.
Cool. I didn't know that. Anybody know anything else about any of these amino acids? Huh?
It's like some of them make polypeptides.
Yeah, they can all make polypeptides. That's good. What else? What else you know about it? Anybody ever hear the myth of tryptophan? What is it? What's the myth for tryptophan? What have you heard about tryptophan?
Just heard the name.
You've heard the name? Okay. Don't remember the context? You might have heard that tryptophan makes you sleepy. You may have heard that after Thanksgiving dinner, you eat turkey, which is rich in tryptophan. That's why you go to sleep after Thanksgiving dinner. All of that is utter nonsense. Tryptophan does not make you sleepy. Okay? You know what makes you sleepy after Thanksgiving? The fact that you stuffed yourself and you're sitting down watching football and you fall asleep. That's what makes you go to sleep, right? In fact, if tryptophan were responsible for that, you would actually fall asleep more likely after eating cheese. Cheese is richer in tryptophan than turkey is. But nobody says, oh, eat some cheese and go to bed, right? So all that stuff that you see on TV about, oh, this tryptophan supplement to help you sleep better, it's just a placebo effect. You might take it and you might feel drowsy and you might go to sleep because you've convinced yourself that you're sleepy and you're going to go to sleep. It has nothing to do with biochemistry at all in reality. Okay, it's kind of nonsense stuff. There are also amino acids that have acidic side chains and basic side chains. Okay, and you can see the codes on these again. Aspartic acid, ASP, that makes sense to me. I don't know why they call it D as the 1-letter code. Tyrosine, I don't know why it's Y, other than the second letter is Y. All of those have acidic side chains. And then the ones that have the basic side chains, my favorite is lysine, L-Y-S. I do a lot of research with lysine, or I have done in the past. And that's because this side chain with the primary amine, although they're showing it as the ammonium salt here, at the right pH you can make that the primary amine. I can modify that. I can do a lot of chemistry with that. I can take proteins and I can put little decorations on them as we used to do because that is a very reactive group. It's a good nucleophile, right? And in fact, the proteins in your body function as nucleophiles and react with things that are derived from sugars, and that's how these things get transformed into other things. Okay. Interestingly, when I started learning the 1-letter codes, I always got lysine mixed up because K, of course, is potassium. right? And so when I'd be reading the one-letter codes when I was taking biochemistry, I'm like, why is there a potassium atom in the middle of this long sequence of amino acids? It's just how my mind was working. So I always have focused on these 3-letter codes. Are any of those amino acids aromatics? Tyrosine, right? There's a benzene ring. It's also what kind of functional group? It's not just benzene, it's what?
Phenol.
Pardon?
Phenol.
Yeah, it's phenol, that's right. So tyrosine turns out to be very important in catalytic mechanisms that you'll learn about in biochem, in some of them. Histidine is also aromatic. That ring, if you count up all the electrons, there's a lone pair on the nitrogen that has the hydrogen. That's 2, 4, 6. There are 6 electrons. Histidine has a aromatic ring. My current graduate student is doing a lot of research on how you take histidine and convert it into other things, which is kind of cool work that we don't have time to talk about today. So there's a lot of work still being done on just these simple little amino acids. Okay? It is very important to remember that your blood pH is important for a reason. Does anybody know what the pH of blood approximately is?
7.35 to 7.45.
Okay, yeah, a little more specific than one. That's around 7.3-ish, right? If your blood falls to 7, are you okay? Are you healthy? No. What about if it goes up to 8? No. You all might look at those numbers and go, that's just a small difference. 7.3 to 7, that's only a 0.3. But you have to remember, pH is the negative log. It's a logarithmic scale, right? So that fraction of a difference is actually a big difference in acidity. If your blood pH changes too much, the structure of your proteins change. And what was the thing that I told you at the very beginning of the semester about organic chemistry? I told you that structure is equal to function. That's why you need to know about how carbon can form bonds, et cetera, right? Structure is function. If I take your protein, hemoglobin, that is responsible for oxygen transport, and I change its shape, what do you think happens? It doesn't carry oxygen anymore, and you die. Okay? You all are alive because buffers exist, because pH can be controlled. Okay? And here's why. So if I take an amino acid, and it's in neutral water, right? So it's the zwitterion. What amino acid is that? The R group is CH3. It's nonpolar. This is alanine. Okay, so we're going to take alanine, and I gave it to Barron. He put it in neutral water. And then I had Gabriel come along and add a dropper full of hydrochloric acid to it. Does it affect the amino acid? You bet it does. Because when the pH goes really low, the amino acid is no longer neutral. It's positively charged. It has a different charge associated with it. Now, if I have Isabella come in and instead add a thimbleful of sodium hydroxide, it's no longer neutral. Now it's negatively charged. The take-home message here is that pH affects the charge of these amino acids. And we know that opposite charges attract, like charges repel. And so if we had a lot of these things linked together and we change the pH, we're going to change the structure. Okay? So that's very, very important to remember. So you need to remember that at lower pHs, your amino acids will typically be positively charged. And at higher pHs, your amino acids will typically be negatively charged. Okay? You have a list in your book of all of this information. We do not have time in this class to go through all of this, but when you get to biochem, you're going to know this chart like the back of your hand. Okay? You're going to have to know how to use all of these things. I can look up the pKa's of the different groups, right? So we know that an amino acid has an amino group. It has a carboxylic acid group, it has a hydrogen, and it's got an R group. There's a pKa for this, there's a pKa for this, and for many amino acids, there's a pKa for the side chain, as we call the R group. Okay? So for alanine, where this is a CH3, you'll notice there is no pKa for the side chain. It's not ionizable. CH3, right? It can't be an acid or a base, it's just a hydrocarbon. But notice the pKa of the alpha carboxylic acid, and notice the pK of the side chain, or of, excuse me, of the amino group is at 9.87. What's kind of odd about the pKa of that carboxylic acid in all of them? What did I just tell you the typical pKa range is for a carboxylic acid? 4 to 5. Now what's the pKa range for all these? Not that. Higher or lower? Lower. By a little bit or a lot? Remember, it's a logarithmic scale, right? So I told you that a typical carboxylic acid that we deal with in organic chemistry is around 4 to 5, and now I'm telling you that all of these are, let's just call it 2. They're around 2. So are these carboxylic acids more acidic than the typical carboxylic acid or less acidic? They are more acidic. Your amino acids are more acidic than the typical carboxylic acid. Can anybody tell me why?
Because the nitrogen is electronegative.
That's right. Yeah. Nitrogen, right? If you look on the periodic table, it's closer to fluorine, right? And so it's an electronegative group, and it lowers the pKa quite substantially, doesn't it? There's other things that go into it, but that's a good enough answer for this class. Okay? So, you know, you all should have looked at this chart and tried to call me a liar. You just lied to us on the last slide. You won't know. The last slide was about pure carboxylic acids. This slide is about amino acids. Okay? And again, we can have the pK of the side chain, and then we have this isoelectric point, the so-called Pi. What's that all about? What's an isoelectric point? What can you tell me about that number for alanine compared to the other pKa's that you're seeing? pKa of the carboxylic acid is 235, pKa of the amine is 987, and the isoelectric point is 611. Huh?
The difference between the two.
Is it the difference? It's close, isn't it?
Is it the average of the two?
It is the average of the two. And it just turns out that they're also close to the difference in this case. But they are the average. So what do you think that tells you about the isoelectric point?
It's the point where the pK is above equal.
Okay. But what does that mean? What do you think that means?
They can balance
Balance? What's balanced?
the carboxylic acid amine.
Okay, but what about them is balanced?
The charges are balanced.
Ah, yes, this is where the zwitterion exists. If I take that amino acid and I place it in a buffer that is at pH 6.11, it will be perfectly in its zwitterionic state, all of it. Is that the same for everyone? No. They all have different isoelectric points, and we can use that to our advantage. Okay, so here's alanine. It's a very simple little equation. You take the two ionizable groups that are most similar. In the case of alanine, you've only got two. You've got the carboxylic acid and you've got the amino group. We know the pKa's for those. You add them up and you divide by 2. 12.03 divided by 2 is 6.02. Now, for some reason, I don't know why they give you this value for this one, and on the other table, they give you 611, okay? But it turns out if you use the right PKAs, you would get, right, so if you use these PKs of 2, 3, 5, and 987, you add them, divide by 2, you get 611, okay? They just used a little different value for the pKa of the amino group here for some reason. Okay. Now, let's look at some different groups, some different amino acids. Here's lysine. Lysine has 3 ionizable groups. It's got the carboxylic acid, it's got the alphamine, and it's got the, let's see, what is that? Alpha, beta, gamma, delta, epsilon. The epsilon. What values are they using to determine the PI? The 2 larger ones, the 2 similar ones, right? So you take the 2 amines in this case, you add them together and you divide by 2 and you get 9.87. At pH 9.87, the carboxylic acid part is minus, and there's only one charge, one positive charge, because only one of those amino groups will be charged at that pH. Okay? One will be neutral, one will be positively charged. So that's 9.87. If we look at glutamic acid, notice they're taking the 2 acidic, the 2 carboxylic acids, and averaging them to get the PI value for that amino acid. Okay? So that's the rule. This is not the final quiz. Don't get excited. I didn't change the slide. I want you all to get together in your groups for about 5 minutes, and I want you to work on those. I want you to look up the stuff in your book, right? And I want you to calculate, don't copy, but I want you to calculate the PI value for those amino acids. doesn't say on there, does it?
Are you looking for the page numbers? 599.
Thank you.
Just another minute. All right, let's go back to the chart. And let's look at asparagine. So we look up asparagine on the table, and we notice that it has a PI of 5.41. Obviously, they are averaging the 8.8 and the 202. You just simply take those two numbers, divide by 2. It's just taking an average of the two values. When we look at arginine, right? That's different. It's got a pKa of a side chain. Which two are they averaging here to get to 10.76?
Two like PKs.
Which is?
9.04 and 12.4.
Yeah, so they're taking those two higher pKa values and they're averaging those. So you can see quite a bit of difference between arginine and asparagine in terms of their PI value, right? And so amino or proteins that contain these different things are going to have an impact on different pHs, of course, okay? So I'm not going to do the other two, but that's essentially what you got to do is go through and find the two similar pKa values and average them, okay? In these cases. All right, why is this important? It is important because when you get to biochemistry, you're going to use this idea of so-called isoelectric focusing. We use this to separate biomolecules. For those of you in forensics, you use this technique to actually identify biomolecules. You may not have heard it be called isoelectric focusing, but you will at some point, okay? So let's take an example where we have an amino acid, okay? And we place it on a strip. Let's just call it a paper strip for lack of a better term. Okay? It's not real paper, but it's close. And let's suppose on this paper strip, we change the pH in it as we go from one point to the next. Okay, so as I move from left to right, let's just say the pH goes from lower pH to higher pH as you move along the strip. Okay? They can manufacture these strips very, very nicely to do this, okay? And we place this strip, as you can see, in a buffer tank, basically. And we hook it to a battery. Positive side of the battery, the negative side of the battery. Okay? And let's say we place this amino acid, let's say it's alanine. Okay? So alanine right here, it's around pH 7 on the strip. Let's just say that's where that's at. And we apply an electric field to it. Well, what's going to happen to that molecule? Is it going to just sit there? What's going to happen? What do you think is going to happen? It'll move. It'll migrate. Yeah, it will migrate. And what do we know about charges? Like charges like to what? Repel, and opposite charges like to attract. Yeah, it's very simple, right? So what's going to happen is this molecule is going to move one way or the other. Okay? So if I'm at pH, let's say I'm at pH 7, so let's put it right here. Right? And let's say it's alanine. Alanine has a PI of 6.02. Okay? What do you think its charge is at pH 7? Yeah, it'd be negative, wouldn't it? It'd have a slight negative overall charge to it, right? Because it's above the PI value, right? So it's going to move. And so if it's a negatively charged amino acid, which way is it going to move on the paper strip? It's going to move towards the positive, isn't it? It's going to move in this direction until what? Not equilibrium. Close.
Until it reaches the isoelectric point.
Until it reaches the pH of its isoelectric point. That's exactly right. So remember, the pH is changing throughout that strip. So this molecule is going to move this way, and eventually it'll get to a point where it just stops, and it won't move anymore. And that'll be at 611 or I say, I don't know why they keep using different values on everything. Okay, so let's just go with 611. All right. Makes sense, right? When it becomes neutral, is it attracted to either? No. Neutral things aren't attracted to either pole of the battery. Now let's suppose we have a mixture, that this mixture also contains, let's see, what would be a positively charged one? Yeah, let's do arginine, right? So if we go with arginine, right, it's going to be attracted to what if it's at pH 7? It's going to be it's going to go towards the negative side because it's positively charged, right? Until what? There. Till what?
It reaches the isoelectric.
Yeah, until it reaches the isoelectric point. Let's just say it's here. And for arginine, that would be at what pH? Around 10.76. So if I place both of those amino acids at the same point and then I apply the electric charge, what did I just do to them? I separated them. I could go in and I could look and see where they went, and I could tell you what that mixture contained, couldn't I? Yeah, very, very easily. This is a nice analytical technique. Now, for those of you going into biochemistry, those of you going into forensic science, you will never do this on just a single set of amino acids. You'll do this on proteins. Proteins also have isoelectric points. So if you want to know if somebody killed somebody with ricin, which is a protein, you can separate it out based on out of whatever else you got based on its isoelectric properties. It's the same technique. It's called isoelectric focusing. It's a nice way to separate biomolecules based on their charge characteristics. Okay? And so you need to know the concept going into biochem, okay, of what we're trying to do here. All right, so that's enough about techniques. Let's talk a little bit about peptides and proteins. The difference between a peptide and a protein is who you talk to. Okay? Me and my colleagues will not agree on at what point does something quit being a peptide and when does it start becoming a protein. All you need to really remember is that peptides have to have at least 2 amino acids linked together to make a small polymer. And that's why we say that peptides are generally between 2 and 50 amino acids that are linked together. Does it mean that if you get to 51 all of a sudden you got to be called a protein? No. Does it mean if you're 49 you can't be called a protein? No. Okay, there's some debate about this. But in general, we consider a peptide to be somewhere between 2 and 50 amino acids linked together. And generally we say that things start to be called proteins when you have more than 50 amino acids linked together to make the biomolecule. Okay? By convention, you're always going to start at the N-terminus, the nitrogen, and you're going to write the sequence to the, what we call C-terminus. And if you look at this molecule would be called glycylalanine. I'm not going to have you name any of this crap, okay? It gets unwieldy. So nobody writes it like this. They write gly-ala. That means that we took a glycine molecule and we took an alanine molecule and we connected them together through what's called a peptide bond. That is this bond right here. Okay? So we took the amino acid glycine and we linked it with the amino acid alanine. Okay, and made a new amide bond. When you get to biochemistry, they're going to call those peptide bonds. I call them amide bonds. They are exactly the same thing. For whatever reason, my biochemistry colleagues like to use different language. Okay? But that is we would call that a dipeptide. Di meaning what? Two. Two amino acids coming together to make a peptide. That's a dipeptide. We can make a tetrapeptide. What does that mean? Tetra, not tri. 4. Yeah, this is 4 amino acids linked together, right? We've got 1, 2, 3, and 4, right? We've got 4 amino acids that came together to build this molecule, okay? Anybody want to take a guess as to what those amino acids are? The first one has no R group, that's glycine. The second one has a CH2OH, that's serine. This one has a benzyl group, a CH2C6H5, so an aromatic ring, that's phenylalanine. And then the last one again is glycine. So this would be gly, GLY, SER, PHE, GLY. That would be the 3-letter codes for all 4 amino acids linked together. So on the N terminus, it starts with glycine, and on the C terminus, it ends with glycine. Okay, so this is a tetrapeptide. You can imagine linking up an infinite number of amino acids to make a peptide of any size you want. Okay? Like I mentioned, the linkage is an amide bond. Your biochem professor will call this a peptide bond. This is a special bond in organic chemistry. Okay? We are polyamide based. Proteins, everything, we are polyamide. We are polymers. We are polyamide. Okay? We are not polyester. We could have been. Nature could have selected us to be polyester based. But it turns out ester bonds are weaker than amide bonds. And that's important. Think about it. Anybody like to sail or anything? I mean, if you like to do that kind of stuff, the ropes you use are made out of nylon for a reason. They're polyamides. They hold up. You do not use polyester ropes. They will rot very, very quickly. Okay? So it's very fortunate that we are put together with polyamides like this. And it turns out that you can draw a resonance structure for the amide bond that's actually quite stable. Okay, so I can draw a resonance structure where I push these electrons here to get this structure. And so it means that the overall hybrid has substantial double bond character to it. These amide bonds don't freely rotate. That lone pair of electrons on nitrogen is going to be in resonance with that carbonyl. And that doesn't exist for esters to the same degree. And so these amide bonds are more rigid than you might expect for a single bond to be. And that's good because it allows the proteins and peptides to hold their shape. Okay? All right. And so when you start to build models of these things, what you'll find when you start to link them all together, when you're using L-amino acids, the natural versions of amino acids, you get the planar backbone where all of the amides are in the plane of the screen, and the R groups will alternate, one coming towards me, one going behind me, one going towards me, one going behind me. They have this alternating, this flip-flopping structure, okay? It's a little hard to see here, but in this particular case, you can see the ones coming out towards me, and then in this case, that one's going behind, because that's the hydrogen coming out towards us, okay? So every other one, because of the stereochemistry, will alternate, okay? And that's important. You end up with different things on different sides. Notice how big the molecule gets. If you all don't have enough parts in your kit to make even this molecule, right? And this is just a simple tetrapeptide. Okay. A couple other things that you need to know here. chains of different peptides can actually interact with one another. Here's an example of a so-called disulfide linkage. Cysteine has sulfur in it, and when two of these get close to one another, they will actually form a sulfur-sulfur bond called a disulfide bond, okay, between two cysteine units. If you ever go to the barber or beauty shop and get a permanent, this is the chemistry they're doing on you. Your hair has a lot of sulfur in it. If you've ever smelled burning hair, it smells like sulfury, nasty junk, right? It's all the sulfur in it. And so if you have naturally curly hair, your proteins are arranged in such a way and held into that shape by these disulfide bonds. Well, if you want to straighten your hair, what do? They put a solution on it. And that solution physically breaks those disulfide bonds so that it will relax and it will uncoil. Likewise, if you have naturally straight hair and you want to add curl to it, you do the same thing. You break the disulfide bonds, wrap it around an orange juice container or something, right, whatever, curler, and then you re-oxidize it back to the disulfide in different arrangements. So this is what happens in the beauty shop. It is actually organic chemistry on protein, okay? And it happens through these cysteine units that can form these disulfide bonds, okay? So you can form disulfide bonds by oxidizing the cysteines, and you can reduce it. And so if you've ever gone to the beauty shop, you might hear them say, I've got to apply the reducer to your hair to start with. That's the first thing they put on when they're doing a permanent. And it smells nasty. It smells like sulfur because it contains sulfur. It's a reducing agent that reduces the disulfides back to the thiols. That straightens the hair. You then take it, you wrap it around something that's cylindrical, and then you apply an oxidizer to it to form the disulfides back. But it's not the same disulfides that get formed. They're in a different shape. The cysteines will be next to different cysteines. And so it will hold the shape for a while, okay? So you can do this oxidation and reduction chemistry on hair quite easily, okay? These also can form rings within these peptide structures. Here's a small peptide called bovine oxytocin. Does anybody know anything about oxytocin? Has anybody ever heard the word Pitocin? It's a brand name of oxytocin. Okay?
It's used for birthing.
It is. That's very good, yeah. So if you're pregnant and you're going to give birth and you're having trouble getting your uterine contractions, they will put you on a drip of Pitocin, which is nothing more than bovine oxytocin. It's a peptide drug, and it causes the uterine wall to contract. How it does it, I have no idea, but it does it, okay? They will also give this to mothers who have trouble lactating because it will help in the lactation process, okay? What do you think would happen if we broke that disulfide bond and reduced it and got rid of it? What do you think would happen to the function of Pitocin?
Wouldn't work anymore.
It wouldn't work anymore. That's right. How many amino acids are there in Pitocin? There's only 9. 9 amino acids linked together with a disulfide bond makes Pitocin, and it looks like that jumbled garb, right? But that's what bovine oxytocin looks like. They have to put you on a continuous drip of this because your body degrades this very, very quickly. And some of the research that I do in my lab and others at this institution do is try to figure out how do we take drugs like this and make them more stable so that we could maybe give you a pill or a shot, not a constant drip, right? So there's a lot of research on how you take these peptides and make them into usable drugs, okay? This is conotoxin G1. This comes from this conch shell or cone snail. You notice there are 2 disulfide bonds in this. So there are 4 cysteine residues that come together to form these 2 rings within the system. This is a toxin that blocks nicotinic receptors, and this is how the snail captures its prey. It injects this toxin to paralyze the fish. The snail then can devour the fish. You know, nature's cruel, but that's the way it is. And it's a peptide-based venom. All venoms are peptide-based. You get bit by a rattlesnake, you're being injected with peptides that cause your heart to stop beating. Okay? That's how this stuff kind of works. But notice there's not a lot of amino acids linked together to make this. Okay? And so how do we know what the structure of these peptides are? We're not going to have time to go through this in a lot of detail. But I can tell you that just 40 or 50 years ago, to determine the structure of one peptide was a PhD thesis, dissertation. It took somebody 4 to 5 years to figure out the structure of one peptide. Today, we can figure out the structure of peptides in about 15 minutes because of the techniques that we have today. And we're not even going to talk about the modern techniques. But the first thing that you've got to do is you got to know what amino acids do you have in that peptide. So you've got to take the protein or the peptide and you've got to break it down into its amino acids. So maybe you've got a protein sample and you break it down and you find out it contains only 5 amino acids. That's important information to know. The next thing you got to do is you got to do this so-called terminal residue analysis. You got to determine what the N-terminus is and you got to determine what the C-terminus is. You got to know where to start and you got to know where to finish, right? And there are ways that we do this. We do this through so-called Edman degradation or through the use of carboxypeptidase. So we can actually knock off that N-terminal amino acid and analyze it, figure out what it is. We can knock off that C-terminal amino acid and determine its structure. Now all we have to do is what? Figure out everything in between, right? We know where we start, we know where we end. I know what amino acids I have. Now I got to figure out how to put them all together, okay? And it's actually a pretty involved process. You'll learn more about this in biochem, okay? But you do what's called partial hydrolysis. You take the large polymer and you break it up into pieces that you can start to manage and see what's in it, okay? And so what they do in biochemistry is they'll take their peptide and they will hydrolyze it with trypsin. And we know that trypsin cuts the protein in half only at lysine and arginine residues. That's what it does. It looks at the entire sequence and everywhere there's lysine it goes clip it. And where there's an arginine it goes clip it. It cuts it up into smaller pieces. I then take those smaller pieces and I subject those to other enzymes that clip at different places. And I start to look at the pieces, okay? Once you have done all of that, you look at those fragments, those little fragments that you have, and you start to do successive Edman degradations. What did the Edman degradation do? They told me what my N-terminus was, didn't it? It knocks off that N-terminal amino acid. So let's say I have a fragment that's got 4 amino acids. Well, I do an Edman degradation to determine that the N-terminus of that small fragment was a lysine. Then I do it again and I find out that it was an alanine. And then I do it again and I find out it's an arginine or whatever. Right? I'm just talking different amino acids here. So we do this and we can piece together the structure. Okay? We're not going to go through a sample problem today. So don't worry about it. So that's all that we're going to talk about for amino acids. We've got about 5 minutes left. I want to talk about a few other things. Okay, we do have a review session on Monday evening at 5:30. I will go through exams 1 through 3. So come prepared to ask any questions about those. The final exam will only come from questions or question types that were on those 3 exams. So if you had a section that you read and that wasn't in one of those exams, it's not going to be on the final. Okay? Don't forget that the final can replace your overall class grade. It is still possible for each and every one of you to get an A. Okay? It's not mathematically impossible yet. What else do I want to say? Oh, the suggested homework problems for Chapter 18. There will be 2 questions out of those problems that will be on the final exam. Okay? So what does that mean for you all? you all should work all of those problems and have those in your notes when you come to the, now, not all of your problems are multiple choice problems like we're gonna have, right? So I've got to take that and convert them into multiple choice questions. Okay, so it won't be exactly word for word, but I'm gonna get inspiration for two of those final exam problems from chapter 18. This afternoon at some point, I don't know because of my schedule, but there will be a chapter 13 quiz in Canvas. You will take a picture of the problem that I asked from 13, you will upload it in Canvas, that's how we're gonna grade that. There will also be a quiz 14, which will be something that I want you to write about your experience in this class. I'll give you a prompt. So if you do it, follow the rules, you get full credit for that one. Okay, so it's there to give me feedback, but also to give you a bonus boost, a little bit, a point boost. Many of you have asked me about the participation points for this class. I go through and I look at your attendance based on your quizzes to determine what percentage of those, I think it's 25 points, that you will get. Those are not bonus points. Okay, it will not say 25 of 0 like the bonus things do. Okay, it is 25 points to the overall, but it's 25 points that you should get. So if I go through and I see that you've attended and turned in every quiz, that's a full 25 points. If you've missed one quiz, that's a full 25 points. I give you one quiz. If you miss more than that, it's a fraction of those 25 points down to a minimum of 10. Okay, does that make sense? All right. Another thing, I don't have the exact time. I think it's 10:45 next Tuesday. Is that right? Look on the schedule. Our final exam will be in here, but it will not be at our normal time. Okay, so it's on the final exam quiz time. So don't be late. You can come early, that's fine. But don't be late. Once we start, we're started and we're on and going. And also I will be sending out a poll as to whether or not you all want a 50-question exam or a 75-question.
Are you going to also make an announcement on Canvas listing when the review for the upcoming final or our review session? Are you going to list the details on that as well as the time for when we're expected to take the final on Canvas?
The time for the final is on the syllabus, so it's already there. Did I send out a message about the review?
Yeah.
Okay, well, I'll send out another reminder, but I thought I did.
It was just with the percent signed in 30. But
It's 5:30, so I'll send out another one, probably tomorrow at some point, so. All right, well, I've enjoyed having you all in class. It's been fun. Hope you learned something. I hope biochem goes well for you. And good luck to y'all in everything. Yeah.
Are you gonna record the review session with your teachers, or I just going over your exams?
Yes, I haven't retired those exams, so I'm not gonna be able to record that. Yeah. Well, clinical chemistry is taught by our department. Yeah, so that's actually taught by the MLS folks. So I've never actually even seen the syllabus for that. But I know that the things that we're covering here are going to be what you need for that class.
I thought so, I just didn't know if you were, since you're not a lot of biochemistry, I don't know what I'm
Okay.
unless if I do.
Okay. Well, you're going to learn a lot about chemistry in the clinical. So it's a big- Yeah.
Thank you.
Yeah. Thank you. Yeah.
Outside of spectroscopy,